Okay, so now we're going to define what a fluid is. We've learned why we want to study fluid mechanics, or at least why you're being forced to study fluid mechanics. And so, a fluid is any substance that deforms continuously under an applied shear. So that is, as long as you keep applying a shear force to it, a fluid, which can be a gas or a liquid, always keeps on. It always keeps on moving. And because it can always keep on moving under an applied shear, fluids can fluids can fill their container, but a solid cannot ever fill the container. And in fact, you could say that a solid is the container. Okay, and so that's really the biggest distinction between a solid and a fluid. And fluids are gases, liquids. A plasma is a fluid for that matter. Loose sand, as long as it's moving, can be considered a fluid. And so there are all sorts of fluids. And so what the consequences of this are is that if you consider a solid, and let's just consider a solid, a bar of metal here that's between two walls, and this wall here is movable. And so we're going to place a metal bar here, and we're going to apply a force to this wall here. Well, intuitively, you would expect that the metal bar will basically jam up the motion of this movable wall here, and it won't move very much. So if we move forward in time, after we apply our force, we'll see at least a little bit of deformation of this wall. It'll basically move to the right just a bit, and it might fatten and get a bit thicker due to Poisson's ratio. But after that initial little deformation, that metal bar will no longer change. Yeah, that's a metal bar, not an Edel bar. And for this sort of condition, where the metal bar stops moving, there is a static equilibrium, and you guys learned in MOM that sigma is equal to F over A for this type of configuration. Now let's take a similar scenario, but sort of think about, like, what if we had a fluid in there instead of a metal rod? So the analogous thing here is a tank, which we have right here. And so the tank has a movable wall here, just like this case over here for the solid, and we're going to apply a force to the right. And in this class, you're going to see this triangle with the three little lines underneath it, and this little triangle means atmospheric pressure. Okay, and so that's what that little triangle means. And so now, what does it mean if we apply shear force, a motion to the liquid water, or a force to the liquid water? What's going to intuitively happen? Well, intuitively, this wall, as long as we keep applying the force, this wall will keep moving to the right, because the fluid can continuously deform to continuously fill the shape of the container as it gets thinner and thinner and thinner. So as we move forward in time, this wall moves to the right, and the level of the liquid goes up because a liquid does not compress very much, and the mass must be conserved, and so the mass has to go up. And as we move on in class, we'll be able to do a very formal control volume analysis to prove things like that. And if we continue to apply the force, intuitively there is no static equilibrium for this case, and instead in this case the water can deform so much that it basically goes spilling out the top. And so a liquid cannot statically resist motion, so it keeps deforming in this scenario. Now, if you close the top here, then that's a different story. But we will get into that stuff a bit later on. Okay? And so that's really the biggest difference between a fluid and a solid, is that under an applied load, a fluid can continuously deform, whereas a solid cannot. A solid can resist that motion, or it can resist that force. Okay, and so I have to go through it. We got to go over the basic unit systems that are used in fluid mechanics. And you guys are all familiar and you know and love the SI system. And there are actually two of them that you might come across in fluid mechanics. One is called MKS, and the M stands for the length unit, which is meters. K stands for the mass unit, which is kilograms. And S stands for the time unit, which is seconds. And you guys know that in this system, the unit of force is called a Newton, and that is defined to be 1 kilogram meter per second squared. Work is just 1 joule, which is defined to be 1 Newton meter. Power is 1 watt, which is 1 joule per second. And pressure is a Pascal, which is defined to be 1 Newton per 1 Newton per meter squared. And in this class, like any other class, pressure will have the symbol P. And density, which will have the Greek letter rho, is just the mass per unit volume, which has units of kilograms per cubic meter. And temperature is both in degrees Kelvin and in degrees Celsius for the MKS system. So, you know, if you need the ideal gas law or something like that, you need to use absolute temperature. If you're just looking for a temperature difference, then degrees Celsius is fine. Now, there's another SI system that you guys may not be too familiar with, but if you, say, after you graduate, if you go work for Los Alamos or for a chemist, or you're an engineer for a physicist group, you will almost certainly encounter CGS. That's where I encountered them. So CGS, it's still an SI system, but they choose the length unit to be centimeters, the mass unit to be grams, and the time unit is still seconds. Now, and you may even encountered CGS in your physics classes. And so the unit of force in CGS is called a dyne, and that's defined to be 1 gram centimeter per second squared. And so now we're going to ask the question, what is the conversion factor between dynes and newtons? So here I'm just going to show you the unit conversion factor. I'm going to go through this pretty fast. But how I do this unit conversion here, I expect you guys to show this stuff on your homework. Okay, oops. So first, we know by definition that a dyne is a gram centimeter per second squared, and so we know, and so we can use that here to get the dyne. Then we convert the mass. Oops, wrong way. We convert the mass from grams to kilograms because we need to get it to SI, or we need to get it to MKS. Then we need to convert the length unit, and that should be 1 meter. Okay, and then we can use the definition of Newton. And when we do that, we find that essentially 1 Newton is equal to 10 to the 5th dynes. Okay, and so essentially, on your guys' homework and things like that, I expect you to explicitly show these unit conversions and how they all cancel out. So here you see the centimeters cancel out, the grams cancel out, the kilograms cancel out, the meters cancel out here, and you're just left with newtons. Okay, it may seem like a lot of work, but this will, especially when we work with the English units, this will help you. This will help you avoid very silly mistakes, which I saw a lot last semester when I taught this, and also even in my graduate level and senior level classes, I see a lot of unit conversion errors, and they're very and they are mistakes that you don't have to make. And now the unit of pressure in CGS is called a Barry, and that's and that's defined to be 1 dyne per centimeter squared. And again, we go through the unit conversion to see how many berries are in a Pascal, and we just go through that. 1 berry, just use the definition, and then we start converting all the dynes and centimeters and everything to MKS. And I just go through this like I did before, and we can start canceling things out. We got dynes here, the berries cancel out, the centimeters squared cancel out here, the meters squared cancel out here, the newtons cancel out here, and we are only left with a Pascal. Okay, and so we find that going through this, we find that 1 Pascal is equal to 10 berries. And the temperature units are for CGS are the same as MKS. Okay, now for the English systems, there is a unit system called British Gravitational, or BG. Force in British Gravitational is a pound force, and mass is a slug. Don't ask me why it's called a slug. It was named by the British, and they have a pretty whimsical naming scheme for just about everything. Okay, and so force in this unit system is simply mass times gravity, and mass is in slugs. And a slug is I keep bumping that. Sorry. And a slug is defined such that a mass of 1 slug weighs a 32.2 pound force minus 1 point, Ryan, you forgot the pound force, at standard gravity, which is 9.81 meters per second squared, or 32.2 feet per second squared. And so what this means is that 1 pound force is defined to be 1 slug feet per second squared. And the units of temperature are in Rankine in the absolute scale, and degrees Fahrenheit in the non-absolute scale. And this is the conversion factor. You guys have all used this in your thermal and your other classes. Now there is the English engineering system, and if you wind up working for almost any American company in the aerospace industry or the rocket industry, etc., you will almost certainly encounter the English engineering system. So you just have to get used to it. I don't like it, but we do need to get you guys used to that. Okay, and so in the English system, mass is defined to be a pound mass, and force is defined to be a pound force. And it's defined such that 1 pound mass produces 1 pound force at standard gravity. Okay, and so we need to think, if we're at standard gravity and we want 1 pound force equal to 1 pound mass, and it's at standard gravity, it's being accelerated by 32.2 feet per second squared, we need to divide it by some conversion factor. And so now we just solve this for this G sub C, which you guys have used in your thermal class, I think. And we can solve for G sub C, and we find that G sub C is 32.2 pound mass feet per pound force second squared. Or you could say that a pound force is 32.2 pound mass feet per second squared. Okay, and so that's how I like to think about it as. I like to think of it as almost like the definition of 1 Newton is a kilogram meter per second squared. Instead, a pound force is 32.2 pound mass feet per second squared. And if you think about it as a conversion factor between pound mass and pounds force, you don't need to worry about explicitly including this G sub C, which some thermal books and sort of how you may have seen it in the past. And in some text, you will see force defined as mass times acceleration divided by this G sub C factor. I don't like explicitly including this. I just like thinking of this as a conversion factor between pound force and pound mass feet per second squared. Okay, and so we'll just go through a little example here. We have an acceleration of 10 feet per second squared and a mass of 16.1 pound mass. What is the force? Well, force is equal to mass times acceleration. We have a mass of 16.1 pound mass, an acceleration of 10 feet per second squared. So we just multiply them together, and we have 161 pound mass feet per second squared. Now, unfortunately, we don't have the proper force units. So we need to convert this pound mass feet per second squared, and we're going to do that using this conversion factor right here. And so pound mass, oops, wrong thing. And so a pound mass, a pound mass feet per second squared is our 32.2 pound mass feet per second squared is 1 pound force. So we just divide by that, and we wind up with the final answer of 50 pounds force. Okay, so pretty straightforward, but you just need to be used to the conversion between force and mass. It's not 1. It's not a factor of 10. It has this goofy 32.2. Okay, but after you get used to that, it's really no different than any other unit system. Okay, and so that's it for the units. Now we need to define a continuum so that we can properly understand when the techniques and analysis methods that you're going to learn in this class are valid, because there are some cases in fluid dynamics where they are not valid. And the assumption that we're going to be making in this class is called the continuum assumption, or continuum approximation. Okay, you will see this called both things. And so essentially, solids, liquids, and gases are usually thought of a continuum. And a continuum is really a material that is devoid of spaces or gaps. And in reality, that's not true, because you can think of even in a chunk of metal. So let's consider a metal rod here. And if you really drill into this and use an electron microscope, something so powerful that you could see all the individual atoms and molecules that are making up this, and zoom in, you'll find that there are a bunch of little. It's made of a bunch of little molecules that are in some sort of crystalline arrangement, but between the molecules, it's all empty space. And so, what makes a solid is that these molecules are so close together, is that basically spring-like forces form between them, and that's part of why a solid can actually withstand the forces, because there are these spring-like forces. But still, even a solid is mostly empty space. And now and it's the same thing for a liquid, only they're far enough apart to where these spring-like forces are not in play. But now, how about for a gas? You would think for a gas that's certainly not true. So let's just consider a compressed air tank. And we're going to drill in again to the point where we can start looking at all the individual molecules that are flying about. Well, for a gas, what makes a gas is that the molecules are basically just flying about, or that the molecules are just basically flying about, basically randomly, and colliding, and then colliding with one another. Okay, and so for this case here, there is a huge amount of empty space between the gas molecules, and so how could an assumption that the gas is devoid of space be even close to physically accurate? Well, let's sort of look at what happens if we define a parameter. It's called the number density, and the number density is the number of molecules divided by per unit volume of which you are counting the molecules. Okay, and so we are going to do that with basically various sized boxes. Okay, and so we're going to count the number of molecules in these boxes, and divide by the box volume. Okay? And again, that parameter is called the number density. So now we got this purple box here. If we're going to use this as our averaging volume, we only have 2 molecules. And if we choose a tiny little box, that is right there, we have 0 molecules. So for this case, ND would be 0 divided by some non-zero volume. And so, our number density is 0. But then as this box grows, we basically if we basically drag the corner, let that disappear. If we take the corner of this box and drag it out to here, eventually we're going to hit 2 molecules. And so the number density is going to jump up just as we hit those 2 molecules. Then we're going to drag this corner out further, and the volume is going to grow, but the number of molecules are going to stay the same. So it's going to be 2 divided by a slightly larger volume. So the number density will go down. Then eventually we're going to hit these 3 additional molecules. Then the number density will jump up, and we keep dragging the corner of the box more and more. And we're going to initially, after we hit those 3 molecules, we will hit none, and the number density will go down because the number of molecules stays the same, but the volume goes up. And then eventually we hit these molecules here, and the number density goes up, and so on and so forth. And we keep this sort of procedure up and up and up until eventually what happens is it doesn't matter how, as long as the box is large enough, like say maybe out to here, the number density, it really doesn't change anymore. Okay? It does not change anymore. And so the continuum approximation is valid as long as we have enough molecules in the box that, statistically speaking, the number density of the molecules in that box is not a function of the box volume anymore. Okay? We cannot use the continuum approximation, say, to analyze the fluid behavior in that very tiny box there that contains 2 molecules. Because you could think, if one of the molecules leaves, we have changed the number density by a factor of 2. But here, when the continuum approximation is valid, we have order 10 to the 10 molecules, and we need to think, well, if a few molecules leave the side of the box or they come in through the side, what is 100 molecules compared to 10 to the 10 or even 10 to the 20 molecules? It is absolutely nothing. It does not matter. And so that's when the continuum approximation is valid. Okay? And so basically the box needs to be large enough so that its delta V, or the size or the volume of that box, contains on the order of 10 to the 10 molecules. If that's true, the continuum approximation is valid, and the techniques we're going to learn in this class are also valid. And for gases, that turns out to be if the box volume, if the side of our box here, where we are counting the number of molecules, is on the order of 10 mean free paths, and the mean free path is just the average distance between all the molecules. Okay? And for most engineering applications that you will encounter, the continuum approximation is valid. 2 notable exceptions are microflows, where you have very, very small channels, like say here. We have a very small microchannel. It is about 1 micrometer in size, and we have a flow of gas. So with this, with these types of systems, is that the length scale of the channel is on par with, say, 10 to 100 mean free paths. And so we can't really treat it like a continuum in that case. Sometimes you can get by with it, and sometimes you can't get by with it. The other case, say for some of you who go work for SpaceX, you might be analyzing systems that come from space and return to Earth. Well, the other common case where the continuum approximation breaks down is in rarefied gases. And the reason being is that in the upper atmosphere, the density is so low and the spacing between the average air molecule is extremely large. And so basically just based our measurement volume for the continuum approximation would be almost on par with the size of the reentry vehicle, especially in front of the shock that is leading it. Okay? And so if you're going to analyze the shock heating and aerodynamics of a spacecraft entering the Earth's atmosphere, so you can analyze the shock, the heating and stuff like that you've seen on TV and movies, then you got to use specialized techniques for that. The continuum approximation definitely does not hold. Okay. And now using this sort of number density idea is the number density is just the mass of all the molecules in that box divided by the box volume, and you take the limit as delta or as the box volume goes to 0, but with the caveat that is still that the box volume, that you're not truly taking it to 0 in the strict mathematical sense. You're just making the box very, very small, but not so small that you violate the continuum approximation. And so basically, the density then is defined as the limit as the volume gets to the absolute smallest that we can possibly take it without violating the continuum approximation delta V prime of the mass divided by the volume of the box. And the mass is just the number of molecules times the mass per molecule. So it is really the number density of the molecules times the mass of each molecule. Okay, that is really all it is. Okay. And density is a function of position. It has the symbol rho, and it's a function of position and time. That is, if you consider a little box, the density can be different. If you consider this tank of water here, where we have water here, and we have air up here. Well, if I pick a point here and ask, what is the density, I'm going to get the density of air. But if I pick a point in there where there is water, then I'm going to get the density of water. Okay, and so the density is going to depend on depend on the spatial location, and it's also dependent on time. So if you poke a hole in the bottom of this tank, the water is going to go gushing out, and if I'm asking what is the density at this point here, initially it will contain water, and so then the answer would be the density of water about 1,000 kilograms per cubic meter. But as time goes on, and the water almost drains completely out, this same point is now in the air. And so at a later time, if I ask what the density is, it's going to be the density of air. Okay? And you have dealt with this in your thermodynamics. And density in general is determined by an equation of state. Okay, and so for gases, ideal, which you guys have dealt with quite a bit. I'm going to zoom in a little bit. For ideal gases, we have P equals rho RT, where P and T are absolute. And P absolute equals P gauge plus P ATM. Okay, so that's just something to remember. Okay, and in thermo, I'm sure you guys, and even when I was a student, I made that mistake quite a lot. Okay, And so just remember that that for the ideal gas law, P equals rho RT. The pressure and temperature need to be on an absolute scale. So that's Kelvin for the temperature, or Rankine, and the pressure needs to be absolute. Okay, and atmospheric pressure is 101,325 pascals, or 14.7 pound force per inch squared equals PATM in the English engineering system. Okay? And for a liquid, you would need to get to that from a table. Rho is usually equal to a constant, which is what we will use for the most part in this class, or at most, rho of a liquid equals a function of temperature. That is, the density of a liquid is normally only dependent on pressure. It can be a function of pressure too, in addition to temperature, but you need really, really high pressures. Like if you're dealing with explosives and things like that, then you need to consider the density of water is also a function of pressure. Okay? And a parameter that we're going to use quite a bit in this class is called the specific gravity. And specific gravity is given by the symbol Sg. Okay? And it's defined, that's what I mean by the sort of triple equal sign here, means defined to be the density of your liquid over the density of H2O. And since the specific gravity is the ratio of two densities, it is in fact unitless. Okay? And the density of water, it's just a relative density is really what it is. If the specific gravity is greater than 1, it is heavier than water. If the specific gravity is less than 1, it is lighter than water. Okay? And so a rho H2O, unless stated otherwise, is normally equal to 1,000 kilograms per cubic meter at 4 degrees Celsius, and rho H2O equals 1.94 slugs per cubic foot at 39 degrees Fahrenheit. Okay, and so if you're dealing with that, that will be the reference density that is used to define the specific gravity. And so just a little example of how you use specific gravity. The specific gravity of mercury is 13.6. Find the density of mercury. Okay, and so here we know Sg of mercury, Hg, is equal to rho of our liquid of choice here, which is mercury, divided by rho of the H2O. And we are looking for the density of mercury here, so let's just solve for that. So this gives that rho of the mercury is equal to the specific gravity of the mercury times rho of H2O. Now in your guys' homework and quizzes, I expect you to work in symbolic form until the very end. Okay, you'll find there'll be some multi-part problems, and if you derive a formula, you can just stick in numbers essentially once, and it'll actually save you time in the end. And you'll learn a lot more about the problem if you work symbolically up to the last minute. And so now we stick in our numbers, and so that's 13.6 for the specific gravity times 1,000 kilograms per cubic meters for the density of H2O, and that gives us a mercury density of 13,600 kilograms per cubic meter. Okay, and in your homework and quizzes, I expect to see units even in these intermediate calculations. Okay, it's because especially for the English system, that will save you lots and lots of silly mistakes. Okay, and another parameter that you'll be using from time to time will be the specific weight. And the specific weight is just the weight of a substance per unit volume. And it's given by the symbol gamma, and it's defined as mass times gravity, which is just the weight, divided by the volume. Okay? Or we can play with this definition and realize there's a mass divided by volume. So that's mass over the volume times gravity. Well, what's mass divided by volume? That is by definition density, and so that implies that the specific weight is just nothing more than rho times g. Okay, and so basically you can look in tables, and sometimes you find specific gravity, sometimes you find specific weight, and just bear in mind what essentially each of them mean. Okay, and so now I'm just going to go over a little example that goes through how to use the ideal gas law and how to set up a problem. So here we are given a little tank of compressed air. The gauge pressure, which would read right there, is 50 psi. The atmospheric pressure is 14.7, and the temperature in the tank is 70 degrees Fahrenheit. And we're also given the gas constant is 53.33 foot-pound force per pound mass degrees Rankine. Yes, these get a little bit weird. And so what we want to find is the density of the air and the weight of the air. And so in your homework, I want you to write given, what you are looking for, and solution. And then also, it's not really appropriate at this point, but we could also write some assumptions. Assumptions will be absolutely crucial as this class goes on, because we will be working with some fairly generalized theorems and principles, and you need to simplify those to make them solvable. And you only simplify based on what the assumptions you are making. So here the only assumption that we're making is that the continuum approximation is valid. Okay, that's really the only assumption that we are making here. And so now we can solve it. Well, we know the pressure, we know the temperature, we know the gas constant. It's an ideal gas. Our pressure is not insanely high, or the temperature is not insanely low, so we can just use the ideal gas law. Okay, and I suppose that could also be another assumption, is that the ideal gas law is valid, which that's also another assumption, because the ideal gas is just an approximation to a much more complete equation of state, but the more exact ones are a nightmare to work with. And so the ideal gas law is P equals rho RT. Well, we are looking for density, so we solve that for density, and that gives us rho equals P over RT. And well, this needs to be in absolute, and we're given gauge and atmospheric pressure. So this will equal to P gauge plus P ATM over RT. And again, I don't want you sticking in numbers here until the very end. Okay, and so now we start sticking in numbers because now I got a formula in terms of all of my knowns. So I just stick it in, and we have 50 plus 14.7 pound force per inch squared. And the gas constant is in foot-pound force. So I'm going to convert this inch squared here to feet squared. So we have 12 inches per 1 foot, and I need to square that. Okay, and then I'm going to divide by RT, and that's 53.33 foot-pound force per pound mass degrees Rankine, and we need the temperature on an absolute scale, so that's 70 plus 459.67 degrees Rankine. And just remember that the temperature must be absolute. And so we can cancel out the degrees Rankine. We can cancel out this pound force. We can cancel out these inches squared here. And what we are left with, this gives us that rho equals 0.3298 pound mass per cubic foot. Okay, and we have the proper units of density, mass per unit volume. If you wound up with something involving a pound force, then you would need to go and apply the rule that 1 pound force is 32.2 pound mass feet per second squared. And now the weight of the fluid, and I forgot to mention what the volume of the tank was. The volume equals 0.84 cubic feet. Okay, and the weight is just equal to mass times gravity. Well, that equals rho times the volume times gravity, and that equals 0.3298 pound mass per cubic foot times 0.84 cubic feet times 32.2 feet per second squared. And now you can see that after we cancel out these cubic feet, we have, oops, it's not pound force, we have pound mass feet per second squared, which is not a pound force. We are looking for weight. Weight is a force, so we need to convert that. And so we know that a pound force is equal to 32.2 pound mass feet per second squared. Okay, and so that second squared cancels out. And I wrote the wrong thing there. This pound mass here cancels out, and this implies that the weight of the air is equal to 0.277 pound force. Okay, and I know it's cumbersome, but I expect you to show all of these unit cancellations. If you have a number in your calculations, there is a unit attached to it. If you have things that are grouped together, like you're just adding one pressure to another pressure, and both pressures have the same units, feel free to put them in a parentheses and just attach the same unit to both. Okay, so that's enough on the units. And so now for we've discussed density. Now we need to discuss the velocity field. And for the fluids, unlike the rigid body dynamics you guys might have dealt with, where you have a clear object and it has a clear velocity at its center of mass. Well, fluids, there is a velocity field, and that velocity field, which I have one drawn here, is a function of space and time, okay? And so you've seen many examples of a velocity field. You just need to look at a weather map of a hurricane or a tropical storm or something like that to see an example of that. And traditionally, the velocity vector, which I use the over arrow to denote a vector, is a function of space and time. Okay, and traditionally the velocity vector is equal to u times I hat plus v times j hat plus w times k hat. Okay, and remember that I, j, k are the unit vectors and the x, y, and z directions. So this means that small u is the x velocity component. A small v is the y velocity component. And small w is the z velocity component. Okay. And so if you know the velocity field, you can just use that function to evaluate what the velocity is as a function of time. Okay. At some point in space. So say we are probing the velocity at this point here, and we plot the velocity on the y-axis and time on the x. Well, after some initial time, in the initial phase, all three components of the velocity of vector are changing as a function of time, but maybe after some period, they eventually reach their nice steady values. And so, if the velocity is not a function of time, the flow is steady. Which implies that the time derivative of any variable is equal to 0. So that could be u, v, w, p, t, rho, etc. Okay? And this has to hold for all variables. Okay? So for flow to be steady, partial of any variable with respect to time must be equal to 0 for all variables. Okay, and then we can also classify flows, and if partial of anything with respect to time is not equal to 0, the flow is unsteady. Okay, and so if the flow is steady, essentially v equals v of x, y, and z. And if the flow is unsteady, it's a function of space and time. Okay? So you can imagine if the flow is unsteady, the magnitude and direction of these vector arrows at a given point may change as a function of time. So basically, at time 1, it may be pointing up, and at time 2, it may be pointing down. But if the flow is steady, then at any point, the magnitude of the velocity vector and its direction no longer changes. Okay, but it can still be different from point to point. Okay, and the other way to classify flows, there are a lot of them, and we'll go over them as we start to proceed with the class, is based on the dimensionality. So flow can be classified as 1 dimension, 2 dimensions, or 3 dimensions. Flows are usually 3-dimensional. You can think of a cloud tumbling in the sky. You have motion within the cloud, up, down, left, right, and forward and backwards, and so it is 3-dimension. And so all realistic fluid mechanical flows are always 3D, but for the purposes of analysis, 2-dimension and 1-dimension can still be very useful. If the flow is 2D, it's a function of only 2 space variables. So it could be a function of x, y. That'd be in the Cartesian system, so it's just a function of x and y. You could have a radial coordinate system where it's a function of r and theta. You guys have dealt with that in your Calc 3 and things like that. Or if you have pipe flow, it can be a function of the radius and the position along the tube. Okay? And sometimes you have 1-dimensional flows, and there the function is a function, or the velocity is just a function of 1 space variable. And so you could consider, you have this case that would be called laminar flow, where this velocity profile is not a function of the position along the tube. So that means the velocity is 0 at the walls of the tube. it's peaked at the center, and the shape of this curve does not matter if I'm evaluating this velocity profile here or here. And so this means that basically anywhere in this tube, here, the velocity is only a function of this radius here. Okay? And so we'll stop there.